Thanks everyone for coming tonight. I've been to Mount Prospect several times and done presentations for them. I lived in Chicago for about 10 years and was a professor at Northwestern. I just recently moved to Clarkson to my new position here and have been enjoying things, but we do these things virtually now, and so I can still spend some time with you all talking to you about science and astronomy, which is something that is very near and dear to my heart. We're going to talk about the aurora tonight. Some of you may have seen the aurora in recent months. They have been very active. We'll talk a little bit about that. But it's been stirring up considerable interest. Many of you may have made trips specifically to remote places in the Earth to see the aurora. And so they are often of considerable interest to people. They're often on people's life bucket lists. And so tonight we're going to talk a little bit about them. There will be lots of pretty pictures, not unlike the one that you see here on the screen right now. These are real photographs taken with sometimes with cell phones and sometimes with professional DSLR cameras, but they are definitely very easy to capture phenomena given the technology that you and I have at our disposal tonight. So we'll have lots of pretty pictures as we go through, but we'll talk a lot about the aurora and where they come from and how they're created. My email address is right there, slarson@clarkson.edu. As Catherine said, we'll take questions at the end. So if you have questions, please do dump them in the Q&A. We'll get to as many of those as we can. Invariably, what will happen is, a couple weeks from now, you'll think of something or you'll read something and you'll wish you had asked me that question. So my email address is there. If you send me an email, I'll do my best to point you at a resource, give you a video, give you a web page, something, or answer your question if I can to kind of help you get the answers to the questions that you have. Okay, and I'll have some reading resources for you at the end, which those of you who've heard me speak before know I always do. So, rightscience.wordpress.com, that's my blog. That's a public-facing blog where I write about science, all kinds of stuff, black holes, search for alien life, gravitational waves, Voyager, whatever strikes my fancy. It is public-facing, it's really there so my mom and my dad know what I do. So hopefully it should be understandable, and there's a lot there, so hopefully you'll be able to find something if you're interested, and you can certainly follow me there on social media. So tonight we're going to talk about the aurora. So aurora is a Latin word that means dawn, and we use it in combination with a modifier. So most of you are probably familiar with the aurora borealis, which are the northern lights, but there is also, as some of you may be aware, the aurora australis, which are the southern lights. We'll talk a little bit about the sun-Earth connection and how the sun is intimately involved in the creation of the aurora here on Earth, and then we'll end and talk a little bit about aurora on other worlds, okay? So the aurora borealis is what most of us learn to call these things. We grow up here in the northern hemisphere, and so we're used to that. And so you see these kind of classic aurora pictures. But if you're from the southern hemisphere, you have friends from the southern hemisphere, then they will be familiar with the aurora australis. And this is a picture of the aurora australis from New Zealand, and they look pretty much just like the aurora borealis do. We'll talk a little bit about the colors. So these are just two different aurora pictures that I've just shown you, and the colors are just slightly different for the physics that were involved in creating the aurora at that time. Most of us are used to the idea of seeing aurora from the ground because that's where we live. Every now and then you'll meet someone who has been flying in an airplane and got to see the aurora from an airplane. But our friends at NASA can see the aurora from above. So this is a picture of the aurora from the International Space Station. And if you go to NASA's YouTube, they have movies of this as the space station's flying over the aurora above the Earth. And they are as equally spectacular as the movies of the aurora from the ground. So if you haven't seen the aurora yet and you don't want to go to Iceland, you can become an astronaut and see them from space. That's your other option. So the aurora are something that you and I, as citizens of the 21st century, are aware of. We have these magical devices, computers and phones that we communicate with and are used to having access to all the world's information. If you go to the library, they will have, many, many books that talk about the aurora and have pictures of the aurora, just like the ones that I've been showing you and will show you more of. But the kind of interesting fact about this is that there was a time not so long ago where we didn't know much about the aurora at all. And indeed, most people in the world were not aware of the aurora. So the kind of awareness reaches all the way back to the 1800s when we first began making expeditions into the northern climes. Certainly, the people who live in the northern parts of the world, and there aren't that many in the very far southern parts of the world, but the indigenous peoples in North America, in the northern parts of Scandinavia and Russia, they all have legends and stories and history of the aurora. But when European explorers started making expeditions, they discovered, oh my gosh, there's this weird phenomena. We don't know what it is, and we've never seen anything like it, right? So this painting is in the National Gallery. It's by a guy named Frederick Edwin Church. It was made in 1865, and it was made based on a recounting of an Arctic explorer named Isaac Hayes. So Isaac Hayes had been a student of Church's, and he went on one of these expeditions to the northern areas and saw the aurora, and he was so struck by them, and of course he didn't have a way to capture them. When he came back, he talked to his former professor, Frederick Edwin Church, and this was the painting that resulted. And the thing that is remarkable to me about this painting is Church made this painting based on a description he was given, right? So imagine you trying to describe the aurora to someone who had never seen it before, and whether or not they could make a faithful recreation of it. And this I think is quite remarkable in how faithful I think it looks. I look at this picture, and I imagine many of you may as well, and be like, oh, that's clearly the aurora, because they've successfully captured what you and I have grown very used to seeing in photographs. The first photograph of the aurora was taken shortly thereafter, just slightly less than 30 years thereafter. This was taken by Martin Brandel, who was a German astronomer and physicist. And so he was on an expedition to Lapland. And so he had been dabbling in photography. Photography was very brand new at that time. Some of you may be aware of the history of photography. They were just starting to take stills and first pictures from the streets of Paris and all of these sorts of things. But Brandel was experimenting with it. And so on this expedition to Lapland, they were trying to measure the Earth's magnetic field. We'll talk about that in a little bit later. But he saw the aurora and he successfully captured this image. It was all black and white. They didn't have color images then. But nonetheless, if you kind of stare at it, it kind of looks like you and I expect aurora to look based on the pictures that you and I have seen. Okay, so this was 1892. So it took more than 60 years before anyone was able to see a color photograph. Okay, and so the first color photograph was taken by J.R. Eyman, and this was published in Life magazine in 1953. So some of you may have some Life magazines down in your basement. The library may have an archive. I don't know if they do, but the Life magazine archive is online, and you can go get this article. And they wrote an entire article about the Northern Lights. And you can imagine the impact that had on the general public. This was the first widespread description of the aurora, and with color pictures that people had ever seen. And so this really kind of ignited in the public's mind the idea that there was this kind of strange and beautiful and, very eerie natural phenomena that you could go out and see with your own eye. Okay, so that was barely 70 years ago, and so lots of you in the audience may have been alive at this time, right? So within your lifetime is really when the world kind of became aware of the aurora. Okay, so what are these things? What are the aurora and what causes them? Well, there's basically three pieces to the story of what causes the aurora. The three things are the sun, what we call magnetic field, specifically the Earth's magnetic field. And then there's atomic physics, okay? And if you remember back to your science classes, your physics classes, your astronomy classes, you will remember or may remember that you have talked about each one of those things at some point. And so what I want to do tonight is kind of weave those back together and tell you how these three things combined lead to the aurora. Okay, so the place it always starts with is what we call the Sun-Earth connection. The sun is kind of one of those very interesting astronomical objects. It's ubiquitous in our lives, right? We go outside, it's sunny, we don't really think about it unless we have to put on sunscreen. But in a very real way, our entire life here on Earth is driven by every single thing that the sun does. The Earth wouldn't be here if the sun's gravity hadn't collected all of the stuff together that became the planets. The Earth wouldn't be warm if the sun wasn't actually shedding energy onto the Earth and heating the planet up. We wouldn't have plants because they wouldn't have energy from the sunlight to photosynthesize and turn themselves into carbohydrates. And if you didn't have carbohydrates in the grass, then you couldn't feed cows. And if you couldn't feed cows, then we couldn't make ice cream, right? Ice cream comes from the sun because of this kind of very intimate sun-earth connection that we have. So in a very real way, the sun drives our lives here on Earth in ways that we don't think about very deeply very often, but it is true. Okay, and the aurora are just another manifestation of the connection between the sun and the earth. And indeed, understanding the aurora has led to a deeper understanding of what that sun-earth connection is. Okay, so the part at the sun where this all starts is that the sun is absolutely shedding light on me and you. But that's not the only thing the sun is giving off. So back in 2017 and again last year, we had total solar eclipses travel across the United States. So this is a picture from the 2017 total solar eclipse. Some of you may have seen this. And when the sun is eclipsed, what you notice is that even though the sun is hidden behind the moon, you can see this enormous halo, what we call the corona, around the sun. And all of that is material that the sun is throwing off and is then being, it's energetic in and of itself, but it's also being illuminated by the sun, which is why you can see it when the moon is in front of the sun. Okay, that energetic material is streaming through space, and some of it streams towards Earth, just like the light from the sun streams towards Earth. And it's this material that we're interested in when we start talking about the aurora. Okay, so NASA has for many years invested, lots of the space agencies around the world, but NASA in particular, has invested in telescopes to observe the sun so that we can understand the material the sun is sending toward us, how it changes over time, how energetic it is, and what the dangers might be. Okay, so I'm going to show you a couple of movies. Hopefully they'll broadcast across the Zoom, but you can find these on NASA's heliophysics sites if you go searching for them. So this is a what we call the active sun. It is a picture of the sun over time, very short periods of time. Okay, and what you see is the sun is a kind of constant moving, swirling, boiling morass of energetic materials. That very bright thing there in the center is what we call a solar prominence. Okay, you'll notice the shape of it. It's round and it has lines. We'll come back to that. But what's happening is material from the surface of the sun is being thrown into space. It's being directed by the sun's magnetic fields, and then it rains back down onto the sun. And you can see there how large these things are. These solar prominences are far larger than the Earth is. Okay, so these are enormously large, they're enormously energetic, and they are just an everyday part of what goes on the sun. Okay, so this right here was called a solar prominence. Material kind of bursts up, it's guided by these magnetic loops, and it makes these kind of fountain-like prominences that rain back down to the sun. Every now and then, you get a very energetic one, which is breaking away from the sun. Okay, so it gets thrown up with such speed and force that it breaks free of the sun's magnetic field and it goes bursting out into space. Okay, this is called a coronal mass ejection. So it's happening above the sun in that kind of halo you could see in the eclipse picture. That's called the corona. And it's a whole bunch of material from the sun. So it's mass and it's being ejected. So coronal mass ejection, it tells you exactly what it is. Okay. So we have satellites that monitor for these things. We see them thrown out into space all the time. And every now and then one will erupt off and it will get thrown towards the Earth. And it's when that happens that we have these gigantic auroral storms, which some of you may have had the opportunity to see. Okay? So all of that material here, yeah, there you go. So there's another, see how it just bursts out the side. Okay? All of that material goes streaming from the sun, which is over here on the right, and it goes streaming towards the Earth. Okay, and what you see in this, this is a artist rendition, is when it gets to the Earth, it kind of breaks around the Earth. Okay, it's like a boat plowing through Lake Michigan, right? The water is all going in one direction, but when the boat hits it, all of the water spreads out around the boat. Okay, so what's causing this breaking around the Earth? That breaking around the Earth is caused by the magnetic field of the Earth. Okay, and it's the magnetic field that both protects us from all of this material come streaming, but it's also the magnetic field that creates the aurora. Okay, so let's talk about the magnetic field. This is the second part of what we need to create the aurora. So to talk about the magnetic field, I did this little demo. So some of you may have played with or remember playing with in science class what we call a bar magnet. Okay, so the bar magnet there is in the, it's underneath a Tupperware. It's painted red and blue, and one side's marked north and one side's marked south. Okay, and so what north means is that if I were to tie that magnet onto a string, the magnet will pivot on the string and orient itself so that the north end is north seeking. It will point towards the north end of the Earth, and that's because the magnet is interacting with the big magnet it can see, which in this case is the Earth. Okay, but for the moment, I just want you to pay attention to the magnet because I want to show you what the magnetic fields are. Okay, so what I'm going to do is when this movie plays is I'm going to spread iron filings on the top of the magnet. So these are just little small bits of iron. And so when they fall on the magnet, each of them becomes like a little tiny magnet, and it tries to orient and connect itself to the other tiny magnets around it, the other bits of iron filings. Okay, and what you see is they form this very distinct pattern. Okay, there are lines that run from the south pole of the magnet all the way to the north pole of the magnet. Okay, and magnets want to line themselves up along those lines. Okay, that's why when you bring two magnets together, one of them sometimes will try and flip itself over so that the north ends and the south ends can stick together. Opposite ends attract in magnets, like ends repulse. Okay, so these magnetic lines or magnetic field lines, or as we say in physics, magnetic lines of force, are shaped just like you can see them here in this picture. Okay? So why is that important? Well, you will often hear it said that the Earth has a gigantic bar magnet inside it. Okay, what do we mean by that? We mean that the Earth's magnetic field looks just like this magnetic field for this bar magnet that I just laid out for you. If I put the Earth over this picture, okay, it's just like there's a bar magnet inside the Earth because the field lines, the magnetic field of the Earth, is shaped on the outside of the Earth, just like that magnetic field in the magnet that I just showed you. Okay, so why is that important? Well, it's important because magnets aren't the only things that pay attention to magnetic fields. The other thing that pays attention to magnetic fields are charged particles, subatomic particles that have electric charge on them. And you probably remember learning about these in science class. There are three classic particles. There's the neutron, which doesn't have any electric charge. There's the proton, which has a positive electric charge, and there's the electron. Okay, those are the three particles that make up atoms, and two of them have charges. Well, as it turns out, in nature, and in particular in the solar wind, you can have free versions of these particles, electrons and protons in particular. And so what happens is when they come flying along in the solar wind and they approach the Earth, they can see the Earth's magnetic field. And what they want to do is they want to follow those magnetic field lines. And so here you can see why it's important that we understand how the magnetic field lines of the Earth are situated. They are aligned along the ends of the magnet, and you see on the Earth's case, they go into the South Pole and they go into the North Pole. Okay, so as the solar wind comes streaming along, some of them follow the outermost portions of the magnetic field out here and go around the Earth. But if some of them get close enough, they follow these little field lines and they end up plunging down to the Earth in the northern part and the southern part of the planet. Okay? So we have this kind of big global picture where some of the magnetic field directs particles around us. They get deflected. Some of it gets trapped into these magnetic field lines and they get driven towards the poles of the Earth. Okay? So that was the second part of the story. And the reason this is important is because those magnetic field lines come down in the north and south parts of the Earth. And when we look at the Earth from space, what we see is the aurora in a big ring around, this is around Antarctica, but there's another one around the northern part of the Earth where the aurora are appearing. And that corresponds to that place where all those magnetic field lines are plunging into the Earth's atmosphere. Okay, so that's part two of the story. Part three of the story is related to why we see all of the colors. Okay, so when you and I look up and we see the aurora, we're not seeing the magnetic fields. Our eyeballs aren't built to see magnetic fields. We're not seeing the electrons and the protons. Our eyes aren't built to see subatomic particles. What we are seeing, however, is light. So somehow this process has to generate light. And some of you may remember this story. The way this happens is a high energy particle, in this case an electron, comes into the atmosphere. It hits a molecule. Okay, and what that does is it causes the molecule to change its state, as we say. It gets energized. It starts moving faster, or it stretches, or it bends in some new way. It absorbs all the energy of the electron when it gets hit. Okay, it's just like when someone punches you, right? You absorb all of that energy. It knocks you over, right? Something happens. Okay, and so this is what happens to molecules when they get hit. They get excited. But molecules don't like to be excited. Atoms don't either, right? When they're in that excited state, they feel very agitated. They like to be non-excited in their ground state, as we say. And the way they calm down is they give off light. Okay, so once the molecule's been excited by all these particles that the sun's throwing at us and the magnetic field is directing down to the Earth, then it gets out of that state by generating light. And that light ultimately becomes what you and I call the aurora. Okay? There are different colors because there are different kinds of atoms in the atmosphere. Okay, and each of the colors that you and I are familiar with when we look at the aurora tend to come by and large from specific kinds of atoms in the atmosphere. So the pinks come largely from oxygen, the blues come largely from nitrogen, the greens from oxygen, and the purples from nitrogen. Okay? So this is where all of the colors in the aurora come from. They are different densities in the atmosphere. So there are kind of places where there's more oxygen and places where there's more nitrogen. The particles' energy changes as they go up and down through the atmosphere. And so the light that's generated also tends to separate itself based on what kinds of atoms we're seeing, how energetic the particles coming in are, which is how far into the atmosphere they can get, a whole bunch of different factors. But in the end, what you and I see then are these curtains. Okay, so these lines are very strong features in the aurora, and then you get this color separation that we were just talking about. So the reds come from, I've already forgotten what the reds come from. The greens come from oxygen, and the reds from something else. Okay, so this is how you get your color banding in the aurora. Okay, So, great, we can see the aurora. Now, if you're paying attention, some of you may be like, well, like 5 or 6 years ago, I didn't really hear that often about aurora, but then like last year we had two big aurora storms that we could see right here in Chicago, right? So why is that? Well, the reason for that is that the sun changes what it does on a regular cycle. Okay. So there's something called the solar cycle. Okay. That's what we call it. It's 11 years long. Okay. And what the sun does is there are times during the sun's cycle when it is inactive, like this part up here. Okay. So we call that solar minimum. The most recent solar minimum was in about 2019. Okay, and if you think back to 2019, so that was the year before the pandemic, I don't remember seeing very many aurora during 2019. Okay, and it's because the sun was quiescent. There weren't that many of those big solar flares and coronal mass ejections. And so the sun's just kind of resting, let's say. Okay. But once it gets done with that, it starts getting more and more active. And what that means for us as scientists is we start seeing more sunspots, we start seeing more solar flares, and by the time we get to what's called solar maximum, and right now in 2025, we are roughly at when solar maximum is expected. The sun is doing all kinds of stuff every single day, including sending off those big coronal mass ejections that we saw the movie of earlier in the talk. Okay, and it's those big coronal mass ejections when they come blasting towards the Earth that make the big aurora that you and I can see down here in the lower 48. Okay, the kind of normal solar, activity up here in the middle of the cycle, that'll produce aurora that you can see when if you travel to the north. So if you go visit Yellowknife or Iceland or go to northern Norway, right, then you can see the aurora just about any time during the solar cycle. But if you want to see it down where you and I live, right, then we're usually looking around these times of solar maximum. Okay? So, why does NASA care about all this, right? Why is it important, right? We all love to see the aurora. We take great pictures. We show them to our friends at the barbecue. We, post them on Facebook. We send them to our aunt and uncle who missed it, right? But that's not a reason really to do science, right? NASA always has a good reason for the science that they do. And in this case, they're interested in what we call space weather, okay? So space weather is all about how our planet and how our civilization interacts with all of this stuff that's happening on the outside of the planet and influencing what's happening on the planet. And in particular, you and I in the modern age are very susceptible to things like space weather from the sun, coronal mass ejections, solar storms, all of these big events from the sun. They send massive amounts of charged particles towards the Earth. The Earth's magnetic field grabs some of them, and we have satellites, we have astronauts, we have electronic devices on the ground that when all of that charged material gets directed into the Earth, it can damage them, overwhelm them, and indeed destroy them. Okay, so there are many famous examples of this. Probably the most famous one in the 1800s, there was an event called the Carrington event. Okay, so there was an enormous solar flare, so bright that people not looking at the sun could see the flare happen on the ground, right? So it was just this gigantic flash of light. But then, so the light got here in 8 minutes, but it took the solar storm, the coronal mass ejection, 3 or 4 days to get here. But when it got here, it interfaced with all of the wired systems on the planet at that time. And you're like, mid 1800s, what wired systems did we have? Well, we had telegraphs. And so the charged particles ran along all the telegraph lines and blew them out. Okay. More recently, in the 1980s, there was a similar event that destroyed, overwhelmed, and sent the power grid in Quebec down. Because all the charged particles went into the power system, it overwhelmed all the transformers, and the power grid went down, right? So even here on the surface of the Earth, it's not just our satellites up in space, right? Even here on the surface of the Earth, we have to worry about this solar weather. So you and I get the benefit of all the cool aurora stuff, but our civilization depends intimately on this technology. So it's a good thing if we can understand this space weather a little bit better. So what about other planets, right? Earth's not the only planet with magnetic fields. It's not the only planet bathed in the solar wind. And so indeed, when we started going to other planets, we have discovered that there are absolutely aurora on other planets. Okay. So this is Saturn. Okay, and so you can see, just like on Earth, there is an aurora oval. So Saturn has some big magnetic field. It's just like it has a bar magnet inside it, and its magnetic field grabs the charged particles and directs them down into Saturn's atmosphere, and it creates the aurora, just like it does here on Earth. Okay. This is Jupiter. Okay, so Jupiter absolutely has auroras on it. Now, the aurora on Jupiter are a little bit more interesting. So Jupiter is the biggest planet and has a huge magnetic field. So some of the aurora here is absolutely from the sun. But Jupiter's environment is very also strongly influenced by its moons. So some of you may know that the moon Io, which goes around Jupiter, is the most volcanic body in the solar system, and it also is throwing all kinds of crap into the Jovian system. And so there's all kinds of plasma and charged particles from the sun and from Io and all kinds of stuff. But nonetheless, they get directed by Jupiter's very strong magnetic field into the northern and southern parts of Jupiter, and you get aurora. Okay. And so there's been a kind of nice, um, let's call it artistic trend in the last several years to build travel posters for all the cool places that we're discovering out in the universe. And so, of course, there's going to be an opportunity someday for us to go to Jupiter and see the auroras on Jupiter. So, I think this would be an awesome travel program. I don't know about all of you all, but I would sign up. So. But of course, we're not really thinking about sending humans to Jupiter. We're not really thinking about sending humans to Saturn, at least not yet. 2001 fans will tell us eventually we'll go to Jupiter. That's certainly true. But right now, what we're really thinking about is going to Mars. Okay, so the question arises, well, what about Mars? Okay, well, traditionally, we don't think of Mars as having aurora. Okay, and that's because one of the interesting features of Mars, it's much smaller than the Earth, is it does not have a very strong magnetic field at all. It certainly has an atmosphere, okay, but it does not have a strong magnetic field. There's lots of kind of reasons for that. There's lots of implications for that. It's one of the reasons that Mars has lost its water over time. There are implications for living on Mars if there's no magnetic field. But in general, as a consequence, you don't have these kind of concentrated areas where you expect to see the aurora on Mars. But nonetheless, MAVEN, which is one of our instruments at Mars right now, has as we call it, ultraviolet spectrograph. So it's an instrument that looks at Mars in ultraviolet light, light your eye can't see, the same kind of light that gives you suntans and sunburns. Okay, and if you look at Mars in ultraviolet on an average day, Mars will look like this. You won't see anything. Okay, but when there's a big solar event, and you look at Mars in the ultraviolet, you get this bright rim of ultraviolet light coming from Mars. And that is the Martian aurora. They are ultraviolet aurora in this case. And it's from all of those particles slamming into Mars's atmosphere all over the planet, okay, and creating what you and I would definitely call an aurora. Okay, so there are absolutely aurora going on other planets. It's often useful, especially in astronomy and physics, to have multiple examples of what's going on. So we understand the aurora on Earth pretty well, but being able to study aurora in different situations with different magnetic fields and different planets and different atmospheres gives us a lot stronger ability to understand what the interaction between the planet and the solar wind is. So these are kind of critical and important ways for us to understand this, what we were calling the Sun-Earth connection at the beginning of this talk. Okay? Okay, so if you want to see the aurora, what are they going to look like? So this is a time-lapse picture from Iceland of an auroral event. You can see cars driving along the highway there on the other side of the lake, so it gives you kind of a sense for what the time lapse are. But the auroras do slowly change over time as you're watching them. And so if you're going to be an aurora watcher, you know, it doesn't pay to just go out and look and then go back inside. You know, you gotta you know, bundle up in your coat and take your mug of coffee and spend time time out there watching for them. That's hard when you live, in Chicago like we do, and the auroras don't happen very often. But if you make one of these special trips, you can see someone over there on the left side taking pictures, right? If you make one of these trips to see the aurora, as long as the skies are clear, like they are in these movies, you're going to get to see them. But they're very engaging, right? They constantly change and they look different every time you look at them, and so you definitely end up spending a lot of time out with them. Now, all of these photographs are taken with DSLR cameras and then stitched together to make a movie. One of the great things that's happened in the last 5 to 10 years is that the camera technology in our phones has gotten much, much better. And so even people like me and you can walk out with our phone and take a picture of the aurora now. And I'll have some examples here in a few slides where I'll show you what my phone shows, and then I'll show you how I tried to back it out and what your eye actually sees. But it's definitely able for people like me and you to get aurora very easily now with the device that you have in your pocket. So these are time-lapse movies, but you can actually, this is a real-time movie. So you can see over there on the left side, you can see the steam rising from that hot spring. So this is all real time, and this is about right for how you see the aurora changing when you're standing out staring at them. Okay, so you'll see the curtains kind of undulate back and forth slightly. You'll see areas get brighter and dimmer on the time scales of 5 to 10 seconds or so. Okay. And so, if you're out when there's an especially active aurora going on, you'll definitely see this happening. But if you're like here in Chicago, where we don't have auroras very often, you may go out and there may not be very active. But if you stand out for a few minutes, then, there will be like, 5 minutes where it gets really bright and you can totally see what's going on. So, but this is real-time changes. This is I think this one's in Norway. So this is the auroras are basically coming straight down on you. So you're looking straight up into the auroral curtain and into the magnetic field that's directing it straight down at you there. So. Okay, so this movie, this is from last October. So we had that big event people in like Florida and Arizona were seeing it. But this is taken from my house in Long Grove. Okay, so I'm still there in the light pollution where you are. I set up my camera on a tripod and I let it run for an hour, taking 5-second exposures, and then I just stitched them all together to make the movie. Okay, so this is an example right there in Chicago. You see the air. I live on the flight path to O'Hare, so you can kind of see the planes going by. But you see the aurora got suddenly very bright. They got very green and red. And for like 10 or 15 minutes they were really bright, and then we had a couple episodes and then they just faded away. Okay, so we got the warnings. I'll talk a little bit about where to get warnings so that you know the aurora coming, but that's what caused me to go out and set it up. And I was so glad I captured it there. Okay, so that was right there in the same area most of y'all are in. Okay, so hopefully this has got you excited. You definitely want to see the aurora. What do you do? Okay. Well, the thing that happens now that didn't happen in the olden days is we have all kinds of access to the data that tells us whether or not the aurora are going to happen. There are apps for your phone. So these are 3 example apps across the front from my phone, just screen captures from my phone. And then there are websites that you can go to. Okay, so there's a Space Weather Prediction Center from NOAA. There's the so-called NOAA Aurora dashboard, and then Space Weather Live. Okay, and I have the Space Weather Live app up here as well. So the things you can see like on the Space Weather Live website are just like the things you can see here in the app. Okay, there's lots of different things that the apps show, and so I've kind of chosen different things for each one of these to kind of show you what the different things are. But the 2 things that most people will focus on are the so-called aurora oval maps. Okay, so this basically shows where the aurora are active right now. Okay, and then the other thing is this thing called the KP index. Okay, so the KP index is a number from 1 to 10, I think 10 is the max, or 9, sorry, 0 to 9, not 1 to 10, 0 to 9, that tells you how strong the aurora storm is. And so for those of us here in the lower 48, the higher the KP index, the more likely it is we're going to see the aurora. And I'll show you a map of that here in a sec. Okay? So the aurora oval Okay, it's usually plotted like this. There's the apps will show one for the north and the south. This is just like that photograph you saw over Antarctica that I showed you at the start of the talk. It shows where the aurora are strongest coming down into the Earth's atmosphere right now. Okay, it looks like it's a crescent shape, but that's because it's cut off over here on this side. This is daylight and this is nighttime. So it's strongest over here in the nighttime, as you might expect. Okay. And then this red circle, okay, is the so-called viewing line. So the aurora are happening really high up in the atmosphere. Okay, so you don't have to be standing under them to see them, but if you're standing anywhere within this red line, you should be able to look towards that aurora oval and in principle be able to see it. Okay, you'll notice this is a quote unquote probability. Okay, so this is what are your chances of seeing the aurora? Where it's black, that's out here. No chances. Okay, as it gets progressively brighter green, you get really good chances. And if the aurora are just really going off, then this will be all white here in the center. And there's definitely a chance of auroras. Okay? Now, what I said you and I have to pay attention to is the thing called the KP index. Okay, so the KP index is how strong is the auroral storm. Okay, and so it's a very general number. It's not a hard and fast rule. I will usually go out and look even if the KP index is low, and that's because of maps like this. Okay, so this is labeled by KP index, okay? And what you see is it draws a circle that looks kind of like that view line you and I were just looking at, okay? So if there's a KP4 aurora storm, that view line reaches all the way to the Illinois-Wisconsin border here. If there's a KP6 storm, it reaches all the way to southern Illinois. Okay, so anytime it's kind of getting in proximity of the Canadian border, I usually go out and look just to see, just in case, right? And definitely if it gets into this 5, 6, 7, 8 range, you should absolutely be going out and looking. It's your chance to see the aurora without having to drive or go to Iceland or, northern Canada or anywhere like that. Okay, so this is kind of a picture I keep in my head, and this is what I use then when I'm looking at one of those apps, right? One of these apps, right? It gives me the KP index. I'm like, oh, well, maybe tonight I'll go out and look. The time here is given in universal time, which is like Greenwich Mean Time. You have to convert to Eastern, and it'll tell you to go out and look, and you can check. Okay. Okay. So we had two big aurora events last year. Okay, so there was one in May and one in October, and people as far south as Florida and Arizona were seeing this. Okay, so these are collected pictures from my friends all around the country. So this is from a friend of mine who lives in Montana. So she's under very dark skies. So she totally could see the aurora, but she had clouds. Okay. And she's like, I'm so glad I went out and tried to see it because she has these just beautiful photographs of the clouds in front of the aurora. So she has these really great photographs. This is a friend in Portland, Oregon. So Portland, right? It's downtown Portland. They totally have the same kind of light pollution that we have in Chicago, and they could totally see the aurora during this event. Okay, and this is a friend of mine in downtown Seattle. Okay, so if you go back to your social media and you look at in May and October, you almost certainly had friends all over the country who could see this event. Okay, every one of these photos was taken using a normal iPhone. Okay. So you and I have absolutely the ability to capture these cool pictures now. Okay, so this is my picture. This is from the May event there in Long Grove. Okay, so you can see the lights from the street lights over here on the trees. Okay, so there's clearly normal light pollution, but this is the picture straight off of my phone, right? My phone's like, whoa, there's all kinds of weird light that I'm not used to seeing, and you get these beautiful, beautiful auroral pictures. Okay, but when I was standing out there, I could totally see this. Okay, and I could tell there was a little bit of pink, and I could tell there was maybe a little bit of green, but this is not exactly what my eye saw. Okay, what did my eye actually see? Well, I took this image and I put it into Photoshop and I backed the color off until it looked more like what I remembered my eye seeing. I went and did it as soon as I got the picture, so I didn't forget. Okay, and so to my naked eye, this is more like what I actually saw. You could see a little bit of the pink, you could see a little bit of the green, and everything else was kind of undulating white curtains. Okay, that's very typical, especially here in the southern latitudes. If you go to the northern latitudes, you go to northern Canada, Alaska, Iceland, Norway, somewhere, then where you're right there where the aurora are the strongest, people report seeing colors all the time. Okay, my wife's from Alaska. You can totally see the colors all the time. Okay, they're never as vivid as your phone's going to give them, but they'll definitely be more vivid than we saw them here in Chicago. Okay. Here's another example, right? So I was seeing those green and purple curtains, okay? And to my naked eye, I could see faint tinges of purple and definitely a little bit of the green, but it was largely white, okay? And then for a while, we had aurora coming straight down on us, and they were totally blue according to the phone. Okay, but when I was taking the picture, I couldn't see that at all. Right, with my naked eye, it really just kind of looked white to me. But I could see all the structure. Right, it definitely was something going on. It was moving. It was changing. But not all of the color that my phone could see could I see with my naked eye. Okay, and again, all of these pictures I just showed you were taken right there in the Chicagoland area. So. Okay, so the real question is, man, I really want to see the aurora. How do I know, right? So you can absolutely rely on, if you have your phone in your pocket all the time, those apps will give you alerts. If they think there's going to be a chance to see auroras in your area, your phone will buzz at you. It'll send you a text message, right? But then people are like, oh, but I go to bed at 10 o'clock and I definitely want to see the aurora. How am I going to do it? Well, we solved that problem during the last solar maximum in 2005 by building what we called an aurora calling tree. Okay, so what this was is it was a group of friends that we all put together who said we definitely want to see the aurora. Okay, and so the rule was if you saw the aurora, so let's see, am I on here somewhere? I'm on this map here somewhere. I'm not on this side. I'm on the other side. Okay, but let's suppose Angela saw the aurora, right? So her job is to call the next person on her circle and call one person on the other two circles to get them going. And then when she calls Sylvina, then Sylvina calls Dick and Jennifer, and then Dick and Jennifer call Rufus and Margaret, right? And then when it gets back to you, then everyone's been informed. Okay? Okay, so we had people who were like, I want to see the aurora, but not if it happens after 11 o'clock. So all of these white circles where anyone is like, I don't care if it's 3 in the morning, call me so I can see the aurora. Okay, but all of these people are like, yeah, I want to see the aurora, but don't call me if it's after 11 p.m., right? So we worked it out so everyone got to see the aurora. And during that year, this was kind of right as, smartphones were kind of coming out. The websites were there, you would get email alerts and stuff. But we all saw the aurora like 10, 12 times that year, and so it worked really well. And so this is one way that you and all of your close friends could arrange it so you get to see the aurora. So okay, well, that's about all I want to tell you. So, what are some things here to leave you with? So, there are very few dynamic experiences you can have with the universe, right? By and large, if you go out and you do astronomy and you look at the night sky and enjoy it, right? The sky looks much the same every night as it does the night before. It changes slowly, the stars rotate slowly over the seasons, but the sky is a very sedate and friendly thing. Yeah. But nothing changes very often. But the aurora absolutely do. Right? You go out and you watch the aurora, it's like watching the weather on a stormy day. The things are moving, they're changing their appearance all the time. And there's very few things in astronomy that you can experience that with. Okay? You absolutely should pay attention. Listen on your social media sites, listen to people who are talking about it. You'll get news alerts, use the app, but you should go out and look. Because if you've never seen the aurora, there's nothing quite like seeing them. And even in the southern latitudes where we are, that kind of, curtain-like ethereal light that they have is very captivating and fun to watch. So I absolutely encourage you to do it if you've never seen them. Okay, and we are near solar maximum, so right now our chances of seeing them are high. That will continue for the next year or two, but the sun will slowly start to decline and head back towards solar minimum. And when we get into that solar minimum, 6.5 years from now, then chances of seeing it in Chicago will be harder, and you'll have to wait till the next solar max, or travel to the northern areas. Make a trip to Yellowknife for vacation, and you'll definitely get to see the aurora. Okay? Okay, so I always like to leave you with a few things to read. This book here by Dan Peterson and Calvin Hall, The Northern Lights, Celestial Performances of the Aurora Borealis, is a coffee table picture book. It's just full of gorgeous pictures of the aurora, right? So if you just like staring at pictures of aurora, this is the book for you. This book down here at the bottom by Lucy Yago, The Northern Lights, is about Christian Birkeland. So Christian Birkeland was a Norwegian scientist who's actually the guy who figured out it's the magnetic field and the interaction of something with the magnetic field that's directing particles into the Earth and causing the aurora. And so he figured that out long before we had spacecraft, long before we understood the sun. And the story of how he convinced the world of it and the kind of challenges and tribulations he faced is really a remarkable one. So that's a really great biography by Lucy there. And then lastly, over there, that Storms from the Sun is a book about space weather, why it's important, how we study the sun, and all of the kind of interesting and different things that the sun does. Okay, so that'll get you started. And that's all I'm going to say. So I'll say thank you for your time. And I will pass it back to Catherine and take any questions you have.
Thank you so much, Shane. That was really cool. That was so interesting. I definitely learned a lot.
Good.
So yes, please, if you have questions, type those in the Q&A and we will just jump right in because we already have some questions in there. First one, how does the solar max of this cycle compare to the prior 11-year cycles?
Yeah, so that's a great question. So one of the interesting things about the solar cycle is we haven't known about it for that long, like kind of like 100 years, 150 years or something. So we only have like, 8 or 9, 10 cycles, something like that to actually measure it against. The last solar cycle was quite interesting because what the sun's supposed to what it traditionally we think it does is it gets active. So you get, all kinds of solar events and you get lots of sunspots and all kinds of stuff going on. And then it starts to decline. And the last solar cycle did this kind of interesting double hump thing, right? So it kind of went up and then it started to go down. We're like, oh, the solar cycle's over, and then went back up again, right? So when you look at the graph of it, it kind of looks like a camel. And so there's a lot of interest right now to know whether or not that's just a weird feature of the last solar cycle, or if it's something weird going on in the sun. Are we going to see it again? So I think right now that's what people are trying to suss out. The last time I looked, I should have looked tonight before we started. So we are approaching peak, and deciding are we really on our way down or not is always the game, because of course the sun fluctuates a little bit, and so you kind of need it to go down for several months in a row before you decide you're over the peak. And I we were supposed to go over the peak over during the summer, and I should have checked to see if we're actually far over the peak or not. But we're just kind of right past the prediction for the solar max. And I think the kind of interesting question on people's minds is this double hump question from the last solar cycle. That's a good question.
All right, next question. The next question actually came in before you talked about this, but I'm still gonna ask it
Okay,
anyway in case you
great.
have any
Yep.
other comments. Are the auroras dangerous in any way to our atmosphere or humans?
Yeah, so that's a great question. So generically, the answer is no, right? So you and I and humans and everything on Earth has lived on the planet for, you know, a bazillion years with the sun throwing stuff at us all the time. And so there are, in addition to the solar wind particles, there are also charged particles from the rest of the universe. We call them cosmic rays coming down onto Earth. And they come down and reach the surface of the Earth all the time. So there's an entire another branch of science called cosmic ray physics that studies them, and it interfaces and connects to the solar science that I was just talking about you at all. But this is something that we have always lived with, and life on Earth has always lived with. Like all high energy radiation, it can impact your biology. And so the kind of rule of thumb that people use is when you take an airline flight, you're much closer to the radiation than you hear on the Earth, but the amount of radiation dose you get on an airline flight is roughly equivalent to what you get from a dental X-ray. So down here on the surface of the Earth, it's really the atmosphere that protects us, and so we don't have any substantive danger from it. There's danger to our technology because it's far more sensitive to it than than you and I are, right? It overwhelms our power grids and can destroy computers and that sort of stuff. That's why we worry about it so much. But that's because technology is susceptible to this kind of electrical energy that it brings to the planet. So,
Next question actually came in twice.
okay.
Can you hear an aurora? Does it make any sound?
Ah, I have heard people, so I have never heard the aurora, but there are people who say that you can. It is a phenomena up in the atmosphere and it is electrical in nature. And so people have often reported kind of crinkling or crackling sounds, kind of static lightning or something like that. I can't remember if I've ever read a scientific paper about that, but it absolutely is reported by people. I've seen the aurora many, many times, and I've never heard it, but there are people who do report it. So yeah.
Next question, why do I see auroras with my phone and not my eyes?
Ah, that's a great question. Because your phone, the camera on your phone is really a bionic eyeball, right? Its sensor is far different than your eye's sensor. Okay, so it does two things in particular that your eye doesn't do. One thing is it sees a broader range of colors than your eye can. Okay, so in fact, the sensors, the digital sensors that we build the phones out of, we have to filter them. We put a little a clear, transparent. It's kind of like a piece of glass or plastic over it that gets rid of all the infrared and ultraviolet light that the sensor can see that your eye can't. We do that so the camera mimics what your eye can see. But the other thing it does is it integrates. That is to say, it collects light and stacks that light on top of itself. And those of you who have experimented with taking pictures with your phone at night, you'll see it do that. You'll tap it and it'll count for 3 seconds. What it's doing is it's adding up pictures over and over again. So what it's doing is it's doing a long-term exposure, which is what your eye can't do. Okay, real photographic film is the same way. If you go out and try and take a picture with real photographic film, you click your shutter and it leaves the film exposed for several seconds. And it's that long exposure which brings out the colors in the aurora. If you could expose your eye for a long period of time, you would see the colors. But the amount of light you get in the short period of time that your eye is looking doesn't stimulate the chemicals that make your brain think it sees color. But the phone absolutely can spend that couple of seconds say, "Oh, I see color." Okay, so it's because it's just a little bit different kind of sensor than your eyeball is. That's a great question.
Okay. Where and when can I go to definitely see the auroras? Is there like a place or like a
I
time of
definitely
year?
want to see it, right? So the challenges with seeing the aurora definitely are weather. Okay, so that's your big number one. And then two is just the activity of the sun. Okay, so if you definitely want to see it, the thing to do is to go to the northern regions. There are many places here in the northern hemisphere, in particular, that cater to people. So and if you look at online travel, right, you'll find trips to Iceland just to see the aurora, trips to Finland just to see the aurora, trips to Alaska just to see the aurora. But the usual deal with seeing the aurora is because of the variability, right? Because the sun's got to be doing something, the aurora have to be active, and the weather has to be good. You can't just go for a night and expect to see it. So most people who chase auroras end up going for a week. I have a good friend from Ohio. She's a total aurora nerd. She loves photographing the aurora. She goes to Yellowknife, Canada every year for 2 weeks, and all she does is photograph the aurora every night. And she gets skunked, half the nights because of clouds or something, but she definitely gets to see the aurora every time she goes. Right. So I think looking for travel opportunities where people are where the travel industry has been built around seeing the aurora is probably your best bet for guaranteeing that you're going to see it. So
How about in the winter season? Can you see the aurora? Does it change depending on the season?
Yeah, so winter season is usually the better time to see the aurora for a variety of reasons. The most notable of which is it's darker for much longer, right? So those of you, so my in-laws are from Alaska. So when we go to Alaska, the sun sets at 2 a.m. and it rises at 6 a.m. Right? So it's there's not very much dark during the summer. So you go in the winter because the sun rises at 10 a.m. and sets at 2 p.m., right? So it's mostly nighttime during the winter months. The atmosphere, the storms and the weather, that's always the challenge in the winter, of course. But there are different parts of the season. My friend who chases aurora, I think she goes in February and March because she thinks the weather in spring is usually better. But you definitely summer, if you're going to the northern climates to guarantee you're going to see the aurora, summer's worse because the nights are short. Okay, so I would say fall, spring, winter, and modulo what the weather is like in each of those seasons is the way to pay attention.
Why do the aurorae move?
Why do they move? So the reason they move, actually, if I go back to that movie, let's go back to the movie that I showed you. Uh, let's look at this one. Okay, so these coronal mass ejections, right? They are not just a smooth bunch of stuff coming to the earth, right? It's just like if you splash someone with water, there's big drops and small drops and big gobs of water and just all kinds of stuff. And these coronal mass ejections are the same thing. And so when they come towards the earth, there are clumps of it that are arriving at earth and hitting the magnetic field and getting split off and being directed down to the poles. And so the reason you see the aurora changing is because you're seeing actually the structure of all of that material coming into the earth and it's changing as it's arriving. And so that's what's causing the kind of constant changes and undulations that you see when you look up at the aurora.
If we get radiation even here on Earth, how do we make sure the astronauts are safe in space and on the space stations?
Yeah, so that's a great question. So we especially worry about this when we think about astronauts spending lots of time on the moon, or when we think about astronauts spending, 300 days flying from Earth to Mars. And so the way to protect astronauts, so in classic science fiction, we imagine bases on the moon being above ground with big bubble domes or something. But the real way to protect astronauts from space radiation on the moon is to build the base underground or cover the base with lunar soil, what we call regolith. The same thing's true when we fly to Mars. If you go read about Mars missions, one of the things they talk about is, well, what do we do if the astronauts are in the middle of a CME when it comes at their spaceship on their way to Mars? And the thing they do is they shield themselves. Well, what are you going to shield yourself with? Well, the most likely thing to shield yourself on the way to Mars is your water supply, right? So they imagine building spaceships that have the water supply in kind of big cylindrical tanks where there's a space weather shelter in the middle where the astronauts could ride out a big radiation storm. So shielding's the answer, and the point is shielding against kind of your everyday solar wind that causes your average aurora. That's easy to do. What's of real concern are these kind of big CMEs that cause these big auroral events that we've been talking about. So that's a great question.
With the aid reduction to NOAA, do you still expect to hear from them like in the past about these type of events and auroras?
Yeah, I think with all the changes in the federal agencies right now, things are highly uncertain. There are definitely discussions and movements and constraints afoot to change what we call the Earth observing system. Whether or not those changes persist or implemented or actually come to fruition, I think is highly uncertain because there are corners of the space weather community which absolutely rely on that data for all kinds of different reasons. And that ranges from folks like NOAA and the Weather Service, it ranges to people who are studying Sun-Earth connection, but it also ranges to things like national defense because we have to understand the space weather if we don't want the GPS satellites to be overwhelmed, right? So I would say most of us are, and certainly at my pay grade, right? You know, you and I out here in the normal world, where it's very uncertain what's going to happen. But in my kind of professional circles and the people I'm connected to and I hear, right, there is lots of discussion about all the different ways this kind of science impacts and is important to different kind of corners of our society that we don't really think about. And so I think if you're a person who's active and really cares about these kinds of changes and is concerned about how they might impact the country, the best thing all of you can do is call your representatives, call up Duckworth's office and Durbin's office and whoever your reps are, and just talk to them and say, look, I'm worried about this, and these are the reasons why, and just make sure they know that people are aware that this can be and potentially is very important to the national interests. So.
All right, I think that was the last question. Let me just double check here. Yeah, and there was a comment thanking you, Shane, for this very educational presentation. And I would like to mimic that comment. It was really interesting. So thank you so much, Shane, for being here. And I want to thank everyone for attending and asking your great questions. Love it when everyone has questions, and you all had great questions. So thank you all for coming, and I hope you all have a good night.
Thank you, everyone. Have a great night.